The paper is OLTP through the looking glass and what we found there. It's a 2008 paper. This paper explores some interesting variants of conventional database systems that one might build that exploit recent hardware trends and speculate on their performance through a detailed instruction level breakdown of the major components involved in a transaction processing database system that is Shore running a subset of TPCC. Rather than simply profiling Shore, authors progressively modified it so that after every feature removal or optimization, they had a faster working system that fully ran their workload. Overall, they identified overheads and optimizations that explain a total difference of about a factor of 20x in raw performance. It's shown that there is no single high pole in the tent in modern memory resident database systems, but that substantial time is spent in logging, latching, locking, B-tree, and buffer management operations. Now let's look at the alternative DBMS architectures. First, logless databases. Log-free database systems might either not need recovery or might perform recovery from other sites in a cluster. Second, single-threaded databases. Since multi-threading in OLTP databases was traditionally important for latency hiding in the face of slow disk writes, it is much less important in a memory resident system. A single-threaded implementation may be sufficient in some cases, particularly if it provides good performance. Third, transaction-less databases. Transaction support is not needed in many systems. In particular, in distributed internet applications, eventual consistency is often favored over transactional consistency. In other cases, lightweight forms of transactions, for example, where all reads are required to be done before any writes, may be acceptable. Coming to overheads of OLTP, authors took a modern open source database system, Shore, and benchmarked it on a subset of the TPCC benchmark. Initial implementation running on a modern desktop machine ran about 640 transactions per second. They then modified it by removing different features from the engine one at a time, producing new benchmarks each step of the way until they were left with a tiny kernel of query processing code that could process 12700 TPS. This kernel is a single-threaded, log-free main memory database system without recovery. Continuing the overheads of OLTP, logging. Assembling log records and tracking down all changes in database structures slows performance. Logging may not be necessary if recoverability is not a requirement or if recoverability is provided through other means, example, other sites on the network. Locking. Traditional two-phase locking poses a sizable overhead since all access to database structures are governed by a separate entity, the lock manager. Third, latching. In a multi-threaded database, many data structures have to be latched before they can be accessed. Removing this feature and going to a single-threaded approach has a noticeable performance impact. Fourth, buffer management. A main memory database system does not need to access pages through a buffer pool, eliminating a level of indirection on every record access. Now let's look at the contributions of the paper. The major contributions of this paper are: first, to dissect where time goes inside a modern database system, and second, to carefully measure the performance of various stripped down variants of a modern database system, and third, to use these measurements to speculate on the performance of different database management systems, for example, systems without transactions or logs that one could build. Authors found that buffer management and locking operations are the most significant contributors to systems overhead, but that logging and latching operations are also significant. Based on these results, they make several interesting observations. First, unless one strips out all of these components, the performance of a main memory optimized database or a database without transaction or one without logging is unlikely to be much better than a conventional database where most of the data fits into the RAM. Second, when one does produce a fully stripped down system, example that is single-threaded, implements recovery via copying state from other nodes in the network, fits in the memory, and uses reduced functionality transactions, the performance is orders of magnitude, almost around 20 times, better than an unmodified system. Now time for PS score. It's a nice and engaging read, so on readability it gets 10 out of 10. It's 12 pages long and seems optimal for the content, so it gets 10 out of 10. It's a 2008 paper and it will be challenging to reproduce the results in a current environment, so it gets 7 out of 10. Industry value is a bit questionable as of today, so it gets 6 out of 10. The paper presents a good experimentation and some nice results on learning meter. It gets 8 out of 10. The overall PS score is 8 out of 10.